everyone, and welcome to this module on Introduction to Continuum Mechanics. Today we're going to discuss the stress power or strain energy rate. You might have come across this terminology in some of the books. So basically, from classical mechanics, you know that if you want to calculate work, so if you have very small elements like the ones you see in here, dW is equal to F force dot dr. And here, you know that W is a scalar value or a zero order tensor in here. Then we have F and then we have R vector. But next, if we want to calculate power or P, then it is the rate of the work. So we take the derivative of W with respect to time. Therefore, we're going to get F dot dr dt. So this becomes F dot v. So basically here, what we are going to do is to calculate this power of all the surface forces here, like T1, T2, T3, and their, TE1 minus, TE2 minus, and T3 minus, as well as the body forces in here. And remember here, the body forces in this book are per unit mass. So that's why we have to, if we have BI, we have to put rho dV in here. All right, so with this in mind, let's say that these body forces here, these forces here, they include the surface forces. So they include surface as well as, body forces in here. So these surface forces are the tractions, and here these are BIs, or these are TEIs, it's better to write. All right, so these TIs are basically times the surface. So we have they applied on, because these are, the traction per unit, unit area. So to find the force, the corresponding force, we have to find your product with the area they applied on, and then we have BI. So here we have the weight per unit mass. So we have to write this as rho dV, where V here is, of course, the volume of the element. So now let's start with calculating the surface tractions, and then we keep on with the body forces. All right, so let's get it started by TE1 in here and TE1 minus. So it is applied on the surface here, and then on this surface. So the surface is x1 and x2. So if I want to write the surface force, so it becomes TE1 times the area. So it is dx2, dx3. It's basically dx3, and this is dx2. So next we have v, the velocity. And this is basically for x1 plus dx1, x2, and then x3. Plus, on the other side, we have TE1 minus. So we have TE1 minus dot dx2, dx3 dot v. then we have x1, x2, and x3. So this is equal to, so we have dx1, dx2, so we can take them out. And we also have te1, which is equal to minus te1 minus, which is equal to minus te1. So this is te1 dot v on x1 plus dx1, x2, and x3 minus te1 dot v on x1, x2, and then x3. And then we have times dx2 and then dx3 in here. So if you look at this expression here, it is basically equal to the definition of the derivative. So I can replace this with the partial derivative of t e1 dot v, t e1 dot v with respect to x1 times dx1, then we have dx2, and then we have dx3. So I can get rid of this as well, and we also have here dv. This is the volume of the element that we have in here. All right, so now let's find what is this t e1 dot v. So basically this te1 dot v is a scalar value. It's because, you know, it is representing this f dot v here. So we expect, so if I replace this, so I get t e1. So instead of t e1, I write t e1, capital T. Then I have v. And I'm going to get a scalar value here. So I can write this as e1 dot t transpose v. And this v here, as I already told you, is going to be e1. So if I get vj, whatever this is, it is vj e1. Otherwise, it doesn't make sense. So because, you know, if I put, for example, 2 in here, then it is e1 dot e2, so it gets 0. e1 dot e3, it also gets 0. Therefore, we have to put 1 in here. The book also used I to indicate that this I can be 1, 2, 3, but finally it can only occupy 1 because otherwise it becomes 0. So I just write it 1 from here. So this becomes equal to, and this is also T transpose, and this is ij, of course, so it is 1j here, and since T is equal to T transpose, so they are the same. So we have E1 dot T1ij Vj, and remember this is Tij. This is not, sorry, 1j. This is not dots in here. So then this becomes T, sorry, it is E1 dot T, since this is T transpose, this becomes Tj1 Vj. Then we have E1 is equal to, so we can take this out, Tj1 Vj E1 dot E1, which is basically delta 1, 1, which is 1. So this is equal to Tj1 Vj. And remember here that we can calculate T E2 dot V and get Tj2 Vj, same as here, and also Te3 dot V is equal to Tj3 Vj. All right, so now we have the power related to the body forces, the surface forces, but we also need the body forces. So P is equal to, so instead of TE1 dot V, we can write as this as the partial derivative of T. So we have J1, 2, 3. So I put I in here. Then we have Vj with respect to x. Here is x1, then it is x2, x3. So this is xi, of course, plus. So before just proceeding further, so I would like to swap I and j's in here. So I get I, j. So this gets v, and then we have I, and then this became j. Next we have rho bi, and here we have vi in here. And remember here we have dv. I just got this. So we have dv, or maybe I can keep this. Then we have, we have dv, then we have vi. So this is p basically. So, and we have vi in here and vi in here, all right? So now we have, we can write this as, so we can take this dv out. So we have the partial derivative of ij vi respect to x j plus rho bi vi, and this is dv. Great. So now I expand this. So I open this. We have the partial derivative of tij with respect to xj vi plus tij partial derivative of vi with respect to xj plus rho bi vi then dv. All right. So if you look at these two terms here, this and this, you can really identify rho tij, rho xj plus rho vi vi. This is equal to rho ai then vi from the equation of motion. So this can also be written as rho dvi dt vi. So based on this, we can write P as rho d v I dt vi plus t. Then we have I j, partial derivative of vi with respect to xj, and then dv. All right, so we have to now identify what is this term and what is this term in here. So for rho d vi dt vi, from conservation of mass, we can write d of dt rho dv is equal to 0. And remember, this is the volume, not the velocity. It's basically, so this is dm. So the d of dm dt is equal to 0. So here, if you write this expression here with dv, you can see that these two can form the conservation of mass, and this can also written as, so if I write the vi, so this is equal to dm, I mean this is dm for example, and this can be written as, so if I do this, if I write vi dt, if I take this derivative, then I have, so it is half of v, sorry, I can write this as, so half of this is equal to half of vi, sorry, dvi dt vi plus half of vi dvi dt, which is equal to vi dvi dt. You can also just ignore this 2 in here, then you get this and this in here, then you get 2 in here, then you have to put half in here, and then finally you, since this is constant, you can take this inside, and then everything gets back to itself. All right, so now we have rho dvi dt vi dv is equal to rho dv, or dm simply, vi dvi, oh sorry, is dm, then we have d vi half dt, and since this is constant we can just take this inside, so we have d of rho dv, if I write this also, rho dv vi half dt, and this is basically equal to the kinetic energy. So kinetic energy is half of mv squared dt. So now we identify the first equation, which is d of kinetic energy dt. So now let's find the second one. Tij, partial derivative of vi with respect to xj. All right, so this is the Cauchy stress tensor. So I can write this as, this is T is equal to T transpose, right? So T is equal to T transpose. This is T transpose Ij, partial derivative of Vi with respect to Xj is equal to, so this becomes Tji, partial derivative of Vi with respect to Xj. And here you see that this is a tensor, this is also a tensor. So it finally forms a JJ. So it is equal to the trace of T transpose del V. And this is the gradient of V. So that's why we write here del V. All right. This can be further, simplified. So if I write, for example, Tij del vi, sorry, partial derivative of vi with respect to xj, and let's suppose that I swap I and j, then you get tji partial derivative of vj with respect to xi is equal to, so this can be written as, so I can break this into two, so half of t ji partial derivative of vj with respect to xi plus half of, again, t ji partial derivative of vj with respect to xi. And again here I swap I and j, so I get half of the first, so again t, sorry, tji, partial derivative of vj with respect to xi plus half of tij, and this is I with respect to xj. And here, since tij is equal to tji, so ij, write this as tji. So I can write this as tji and write this as half of. This is basically del v, and this is del v transpose. This is, del v transpose, and this is del v. So we have half of del v transpose plus del v. This is the symmetric part of del v, or the rate of deformation tensor. So this is t j I d I j, and this is basically equal to the trace of t d. Great. So now we figured this out, and we found this is equal to the trace of td. We also show this by ps, and we call this the stress power, because this is this kinetic energy and this is the stress power, or it comes from the strain energy. That's why we call this the strain energy rate, because it is power, so it is changing with time. The rate here indicates the changing with time, and then we have the kinetic energy, and then we have this strain energy, which is due to the deformation of the continuum. So this is also the philosophy under the name, or behind the name. And then we also would like to write this down, the stress power, or PS, in terms of, so right now we found stress power, TD, in terms of, let's say, Cauchy strain tensor, stress tensor, and also D, the rate of deformation tensor. But let's find PS in terms of first Piola-Kirchhoff stress tensor. All right, so we know that from the previous module, we know that the dt of dx is equal to del v dx. And remember, this is in a spatial coordinate. We also know that f is equal to d small x dx. Therefore, here you can write dx is equal to f d capital X. So if I substitute 1 in 2, so 1 in 2, then we have d dt. Instead of dx, we have f dx is equal to del v. Then we have del v dx. And this dx is again f d capital X. So if I expand this, this is d dt f df dx plus this is f dx dt, d dx dt, and this term is basically 0. Why? It's because dx is in the material coordinate, and for the first Piola-Kirchhoff stress tensor, we had the constant d capital X, so its derivative is 0 because it is in the material coordinate, it's in the reference configuration. So then we have also dv f dx in here. So if we compare these two, we can conclude that the f dt is equal to del V F, or df dt is equal, df dt f inverse, of course, is equal to del V f inverse, which becomes I, so we get rid of this. Therefore, we have del V as this, and we can write PS. It was the trace of T transpose del V, right? So now we found del V, which is df dt f inverse, and we only need to identify T0, transpose. So we have to write T transpose in terms of first Piola-Kirchhoff stress tensor. So 1 divided by J T0 F inverse, transpose. Therefore, this is T, of course. So T transpose is 1 over J. So this actually remains intact. So we have F transpose, then we have T0 transpose, and this is FT transpose, so it becomes F, and then we have T0 transpose. So from here, PS is equal to 1 over J, so this constant we can take it out. The trace of, then we have F T0 transpose df, this in here, dt f inverse. So we know that if I write this in here, so trace of f T0 transpose df dt f inverse is equal to the trace of T0 t df dt f inverse f. So if I just move this to this side and then again this to this side, this is equal to the trace of so this is equal to the trace of df dt f inverse f T0 transpose, which is equal to the trace of f inverse f T0 transpose df dt. So from all of these, the one thing that really helps us is this one, because this becomes I. So we replace 3 in here. So we get 1 over J, the trace of T0 T df dt f f inverse f, which becomes I, then this becomes this. So now PS in form of second Piola-Kirchhoff stress tensor is this. All right. You can also write J in terms of rho and rho 0, because you know that rho 0 is equal to rho J. So we found this in chapter 3 of the book and second module. So if I replace J with 1 over J, it is rho 0. This can be written as also rho divided by rho 0, trace of this in here. So also PS is equal to rho divided by rho 0, trace of T0 transpose df dt. All right. So now let's find power stress, the stress power in terms of second Piola-Kirchhoff stress tensor. All right. So here we have PS equal to the trace of T transpose D here, sorry, TD, and it is equal to the trace of T transpose del V in here. And we also know that T is equal to 1 divided by J F T tilde, the second Piola-Kirchhoff stress tensor, F transpose. So from here, PS is equal to the trace of 1 over J F T tilde F transpose. Then we have D. So again, using this property in here, I can write this as the 1 over J. I can take this out because it's a scalar. Trace of T tilde F transpose D F. So now I have the second Piola-Kirchhoff strain tensor and then a stress tensor, and then I have to find F transpose DF. So what is F transpose DF? So we have two proofs in here. So proof one, actually it is the same as the book. So from module 2 and also chapter 3, you know that you have dx1 dot dx2 minus d capital x1 dot d capital x2 is equal to 2 dx1 dot e star dx2. So if I select dx1 equal to dx2 as d small s n, and d capital X1 equal to d capital X2 equal to d capital S M, then what I have is ds squared minus d capital S squared is equal to 2 dx1 dot e star dx2. So if I apply the derivative, the material derivative operator in here, so I'm gonna get d of dt ds squared. So, and this is going to be equal to, so this is going to be 0 because, as I already mentioned, this dyad of the second Piola-Kirchhoff stress tensor is in the reference configuration, so it is constant. So here we have the derivative, the material derivative, its material derivative is 0, is equal to, so sorry, here we have dx1 equal to dx2 equal to this, or equal to dx. So this becomes 2dx dot e star dx in here. So then what we have is 2, this is constant, so dx dot d e star dt, and this is also constant, so this becomes dx again. So I mean, so if you take the derivative of dx dt, then you have e star dx, this becomes 0, therefore the whole becomes 0, and this is also the same for this dx in here for the second one. So then you end up with something like this. So if you take the derivative of this, you get d dt ds squared is equal to, so you have 2, let me just write it here. So 2 ds dot d of ds dt is equal to, here we have 2 dx dot d e star dt dx. So these two cancels out with this one. And also we know that ds dot d ds dt is equal to dx dot d dx. This is also another equation that we derived in the book. Alright, so we get dx dot d dx equal to this equation here, dx dot d e star dt dx. So now we're going to replace dx with f d capital X. So we have f d capital X dot d, then we have f d capital X. So we can write this as dx dot f transpose df dx, which is equal to d e star dt dx. Oh, sorry, I got this dx in here. So this is d e star dt dx. Therefore, if we compare these two, you can see that d e star dt, so maybe this is f transpose df. But I guess that the second proof is way better than the first one. It's quite straightforward, and you don't need to memorize or to derive any other, equations here, because this is somehow very tricky, and you have and it doesn't just stick in your mind. So we start with e star. So we know that it was half of c minus I, where I was the identity tensor, and here c was the right Cauchy green deformation tensor. So here we can write e star as half of, so c was f transpose f minus I. So if I apply this, the material derivative operator in here, so if I also just take this here, so this becomes d e star dt is equal to half of, then I have the derivative of this, so it becomes d f transpose dt f plus f transpose df dt, and then the derivative of the identity tensor with respect to t, since it is constant, so it becomes 0. Right, so now we have to find this df dt in here. So we also know that df dt is equal to, since we have d of dx d capital X, sorry, dt is equal to, this becomes dx dt times 1 over dx, plus then we have d of dx d capital X in here, since it is constant, so it becomes 0. This is equal to, this is d dx dt, and it is nothing but, it's here, so maybe 2 here, del v dx. So from 2, we know that this is del v dx, sorry, dx divided by dx, which is del v f, of course. So if I have df dt transpose, it is equal to del v dot f here, transpose, sorry, del v f transpose, which is equal to f transpose del v transpose. So we have d e star dt equal to, so now we have df transpose is half of f transpose del v transpose, plus then we have f transpose, instead of df dt we have dv f, and I already missed this f in here, so we have also f here. So here you can see we have f transpose del v transpose f plus f transpose again del v f. So I can take out this transpose. I can also write this as F transpose, then I have half of del V transpose plus del V. Then I have F, and this is nothing but D, or the symmetric part of the velocity gradient. So D E star dt becomes 1 divided by 1 divided as ft df, and ps becomes 1 divided by g, was equal to the trace of let's say it's here. So trace of t tilde, then de star dt. And since, if I remember, let me see. So j was 1 divided by j was rho over rho 0, rho over rho 0. So ps is equal to rho divided by rho 0. Then we have t tilde de star dt. And this is the stress power for the second Piola-Kirchhoff stress tensor. And remember here that for Cauchy stress tensor, we had T with D. Here we had T0 for the first Piola-Kirchhoff stress tensor. We had F. And here we had T tilde with E star. We call this actually conjugate pairs. And remember, for the stress power, we have to, so for the stress power, since this is, the rate, so we have T with D. So since D itself is the rate of deformation, it comes from the symmetric part of del V. So it doesn't need this dot in here. It already has this dot or the rate inside itself. We have T0 with df dt, or f dot, and here we have t tilde de star dt, or e star dot. So for the stress power, these are the conjugate pairs, and for the stress power, remember that these are dots, so these are the rates of these deformation tensors. It's very, very important.